For 40 divided by 37, you will always find 1.08, which is the magnification factor. Now, if you want to find the true object size, how do you calculate it? Using the equation we discussed, which states that the magnification factor equals the image size divided by the object size. All right, you have obtained the magnification factor from the equation, and you are able to obtain the image size from your screen or your device, such as from the display. So, if you want to know the actual object size, you will divide the image size by the magnification factor to get your real object size, in reality, as though you are dividing it by the amount of magnification that occurred in this manner. Is this explanation clear to you? Now, when we talk about the reasons, as previously discussed about the magnification, it significantly affects the subject because it is related to the distances between the focal spots or the source and the image receptor and the object and the image receptor. Therefore, the penumbra regulates this aspect, which in turn affects the overall outcome of the issue of geometric unsharpness. The penumbra, as we discussed, is considered similar to the blooming or the spread that occurs. One of the causes of the spread is something called geometric unsharpness, and there is also image receptor unsharpness, movement unsharpness, and edge unsharpness. Geometric refers to something related to the acquisition itself, such as how close the object is to the image receptor or how far the object is from the image receptor, like the focal spot size. For instance, the size of your focal spot affects the resolution. If we say that the focal spot size here is large, if my focal spot size is small, there will be a difference because in this case, if your focal spot size is large, the radiation coming from the focal spot will not reach it because you are talking about a finite or very small focal spot size. Therefore, the produced beam intensity of radiation on your object size will be affected. Regarding your device, it will come from a very small object size, but if your device increases in size, this will cause your penumbra because the same image will be exposed to part of it, while another part is exposed differently. Therefore, this is what will cause the issue with the penumbra. So, the larger you make it, its size increases as the geometric unsharpness or penumbra increases. If we say that the distance between them increases, which is related to the focal spot, then the same idea applies. You are getting closer to your area, and it will enlarge. There is a direct proportionality relationship between the focal spot size and the distance between the object and the image receptor. Conversely, there is an inverse proportionality between the focal spot and the object itself, which relates to the distance with geometric unsharpness. This means that the farther your object is from the image receptor, the greater the distance between the focal spot and the object, which reduces the existing unsharpness, therefore increasing the focal spot size. And the distance from the object to the image receptor increases geometric unsharpness, which reduces blurring and resolution. A larger focal spot size increases geometric unsharpness, which increases the penumbra and decreases resolution. Here, in small focal spot size and large focal spot size, their effect on the penumbra is clearly visible in image A. In image A, with large focal spot size, the penumbra area or geometric unsharpness area is larger than in image B due to the focal spot size being smaller. This is the equation we were discussing a moment ago. So we talked about the factors that affect geometric unsharpness. Now, if you want to calculate geometric unsharpness, how do you do it? You need to know the focal spot size, what its size is, whether it's 0.5 millimeters, 0.1, 0.3, or whatever, depending on the X-ray modality. You should know that the distance from the source to the image receptor is typically 100 centimeters, which is the standard. You should also know that the distance between the object and the film is 1 centimeter. In this case, you know the focal spot size and the SID, as well as the object to film distance. Now, what you will do in this simple area is multiply the focal spot size by the object to film distance and divide by the focus to object distance. How do you find the focus to object distance? You subtract the SID from the focus to object distance. How are you going to get it? Are you going to subtract what? The SID. The object to film distance gives you the focus or the focal spot for the object distance, which is 99 centimeters in this case. This will result in a geometric unsharpness of 0.005 millimeters, which is the amount that will occur in your image. This is the amount that will happen in your case, the amount of blurring that will happen in your images, right? So you can know how much blurring your machine will produce, okay? Or the level of unsharpness, we are asking how much is slightly present in it. The topic of unsharpness or blurring has an effect on small size objects. The smaller the size of the object, the more visibility decreases with increased blurring. When blurring occurs, it reduces the contrast of the small object. And at the same time, it also decreases the visibility of low density objects, which have low physical density. Small size objects are more affected by unsharpness or blurring effects compared to high density particles and large size particles. We are in a large quantity. There are things related to the topic of unsharpness and the topic of resolution, as I was just discussing with the doctor. For example, when we talk about the number of pixels in a digital image and the matrix related to TFT and the number of pixels present, this affects the amount of resolution available. The topic of pixel size, whether it is large or small, all relates to unsharpness and pixel density. If the number of pixels is large, then the number of pixels increases and my resolution increases. However, if I have a large number of pixels or a large pixel size, especially in additional images or in TFT, this will reduce my resolution. Even though it will increase sensitivity, it will reduce my resolution. Now, in the case of screen radiography, is it thick or thin? If it is thick, it will increase sensitivity, but will reduce resolution. When it increases sensitivity and reduces resolution, in this case, it will increase the unsharpness present. If the technology is advanced, then in this case, you have enhanced the technology. If the technology is limited, then you have reduced the technology, but also diminished its effectiveness. Well, the technology refers to the movement of the person themselves. For instance, if the person's movement is vertical, meaning in the direction of the incident light related to the specific technology, then the effect will be independent and can be overcome. However, the problem always lies in the effect or movement, which could be, for example, sliding in the X direction rather than in the Y direction. This movement causes unsharpness. There should be no effect, which is why, for example, the partition must be in a comfortable position for him. If there is something related to breath holding, all of this helps to minimize my movement during the imaging process. The less movement there is, the more it helps reduce movement, especially in certain cases. Now, if you want to calculate the geometry, or I apologize, the movement unsharpness or the motion blurring that occurs, you need to know the velocity at which the object is moving and the exposure time, or how long it moved. You start from the relationship between speed, distance, and time. For instance, if you know that it moved 4 millimeters per second and your exposure time is what it is, which is approximately indicating the exposure time during which it moved, then in this case you would say that I have the speed equals distance. In terms of time, if you want to know the distance over which blurring occurs in your image, if you know the speed, you can determine the exact distance precisely in millimeters. These factors will significantly affect the quality of your image and will cause the blurring effect. If I also have this means that it will be high here and it will start to affect what the grades that will appear to me will decrease, and this will also cause the presence of unsharpness, or it will increase the blurring effect and reduce what is present. The idea of having something called distortion artifacts occurs if the object you are imaging is not aligned with the imaging receptor or the X-ray. What happens is that there will be magnification because it was close to the X-ray in a certain direction. On the other side, there is another side that is far away. For example, if we come here and look like this, we will find this part. This part, for example, is as if the patient or the organ is not parallel to the image receptor. So this part experiences magnification, while this part does not experience magnification or is not in the same arrangement, which causes distortion in the image. Alternatively, the image receptor itself may not be aligned under the patient or under the scanned organ. When I perform the scanning, this also causes image distortion, and you find that some parts experience elongation, some experience shortening, or some experience magnification, while others do not. This idea relates to the fact that the alignment is not maintained during the entire process. All the factors I mentioned are related to how we have deviated and started to experience new effects that impact the resolution and contrast present in the images. Here is the table. I just want you to take a look at it. It discusses the relationship between milliamperes and how you want to ensure that the output remains consistent. If you increase the milliamperes, you can reduce the exposure time because, as I mentioned, the effective milliamperes result from the multiplication of milliamperes and the time, which gives you the effective milliamperes. Therefore, if you decrease the exposure time, you can increase the milliamperes, or conversely, if you increase the exposure time, you can reduce the milliamperes. The kilovolt, kV, is related to the 15% rule we discussed earlier. If you increment the kilovolt by 15%, you are effectively having your milliamperes, or you can reduce the kilovolt by 15%, which allows you to double the milliamperes, resulting in a multiplication that affects the exposure for the image receptor. The same idea applies to the relationship between the source to image distance if you increase this distance. In order to maintain the exposure reaching the image receptor, you need to increase the milliamperes you are working with to keep the exposure consistent. The relationship between milliamperes per second and source to image distance is directly proportional to the square of the source to image distance. Therefore, increasing the distance requires you to increase the milliamperes per second. Regarding elevation thickness, an increase in thickness of 4 or 5 centimeters requires you to change the milliamperes by a factor of 2, meaning you multiply it by 2. As for the grid conversion factor or grid ratio, increasing the grid ratio necessitates an increase in milliamperes per second. The grid has a significant impact on the resolution of the images, especially in screen film radiography. Here, the grid is always very important in the topic of imaging. When I come to perform imaging and I have the image receptor, as we can see, there is a grid between the patient and the image receptor. This grid is made of high-density material forming a network placed under the patient. This network has holes that allow certain elements to pass through, and it has something called a fixed point. For example, let's assume I have this shape. The entire part that I have heavily shaded here, I call it like a grid. What does grid mean? It means that right now, for example, I will allow these holes to let through only the radiation that is incident and perpendicular to my film, while the radiation coming at an angle, like scattered photons, cannot pass through. I'm sorry. This is coming from a Doppler source. It can enter from here, but the radiation coming at a specific angle starts to hit the grid, which has a certain thickness between each hole that is enough to stop it. This improves the contrast, but on the other hand, it reduces the enhancement of the contrast, so you need to increase the milliampere or provide examinations that contain a grid. But on the other hand, let me tell you, look, you improved in the... He told me that, I said, that's it. So you need to increase the milliampere or increase... That's why in examinations with a grid, you find that you need to increase the exposure because your scatter is going to be removed. So the number of photons in the image receptor will decrease. To compensate for the lack of photons in the image receptor, you need to increase your milliampere or your exposure. For example, in children, it is preferable to remove the grid. If it is removed, in this case, because you don't want to increase the exposure on the child, the resolution is not a big issue for you. So in this case, you don't want to increase the exposure on the child, so the grid is removed. But in regular cases, having the grid reduces the scatter of radiation and allows only the perpendicular incident or perpendicular radiation to be incident on the image receptor or received by the image receptor. This is what I call a lead strip, or the grid I mentioned. Now, there is something called a grid. This grid has a certain height, and these holes have a certain width. The ratio between height and width is called the grading factor. Therefore, as your width decreases, this is what I refer to, and consequently, as your height decreases, in other words, your width, the smaller it is, means you have increased the resolution, so your grade factor is high. Therefore, you need more exposure or more milliampere to maintain the exposure. That reaches the image receptor. And this is what I showed you. In the case of increased exposure, you need to increase the milliampere to maintain the image receptor. You need to raise the milliampere to compensate for the exposure reaching the image. Here, you find the relationship that indicates there is both a stationary and a moving grid. If there is movement, it helps. However, if there is a problem with the movement or the rest, it creates issues because the grid itself, if there is a beam falling on it, will absorb that beam at that moment, which will affect the film. So, I have a problem with part of the film not being exposed. It is said that I move the grid. This movement of the grid is necessary so that the part that was covered by the grid or the lead strip moves away from it. Thus, the incident radiation or radiation that reaches the film will be affected. If there is a problem with the movement, this creates grid artifacts in the image. Let's stop here. We can continue after a break. There is no problem, and we will talk about the artifacts. It's not a large lecture, but we will discuss the artifacts present so that we can address the entire topic of image quality. Today, I am here to discuss the topic of motion artifacts, which are disturbances that can occur in images or videos due to movement during the capture process. These artifacts can affect the quality and clarity of visual content. Additionally, I will be exploring the concept of the grid, an essential element in the composition and alignment of visual media. The grid helps organize content and can influence how motion artifacts are perceived. By understanding both motion artifacts and the grid, we can better appreciate the challenges and solutions in creating high-quality visual content. Could you please tell me which chapter we are currently discussing, Doctor? I apologize for not being attentive earlier, as I might have missed the specific details or the exact chapter number that we are supposed to be focusing on right now. It would be really helpful if you could clarify this for me, as I want to make sure I am following along correctly with the rest of the discussion. Is it the one here? Or the one in the book? The one that is like the ghost image, right? Is this found in the FRCR physics notes? Or in another book? Okay, I will give them again, and even if it's not included, it's fine. We can talk about them later on, no problem. I tried to include many of the references available, even those not in the FRCR physics notes, and other things from outside, but if there's something not included in this part, we can discuss it, no problem.